The first interstellar object, 1I/Oumuamua, defied expectations. Detected in October 2017 by the Pan-STARRS Survey Telescope in Hawaii, it was unlike any comet or asteroid seen before. It was relatively small, about 400 meters long, but its shape was extraordinary, perhaps 10 times as long as it was wide, like a cosmic cigar or needle. As it tumbled through space, astronomers noticed its brightness would swing wildly, implying a dramatic elongation and irregular shape. There was no visible coma, no tail, no obvious jets of gas venting from its surface. Oumuamua appeared inert and rocky, prompting debate. Was it a fragment of a shattered planet? A dried-out comet that lost its ices? Its surface was slightly reddish, hinting at long exposure to cosmic rays in interstellar space. It traveled a path suggesting it came from the direction of Vega and Lyra before drifting for hundreds of millions of years through the galaxy. Upon slingshotting around the sun, it sped back out, headed toward Pegasus, never to return. One more puzzle came from Oumuamua's behavior. As it exited our solar system, it sped up slightly, a tiny but detectable non-gravitational acceleration. Typically, comets do this by venting gas and dust like a rocket, but telescopes saw no such outgassing clearly. This mystery led to a whirlwind of theories. While most scientists concluded a hidden comet-like activity, perhaps releasing invisible hydrogen or extremely fine dust, was nudging it, a few voices speculated more exotic possibilities. Could it be artificial, a derelict spacecraft, or a probe sent by an alien civilization? The notion captured headlines, though nearly all experts assert that Oumuamua was natural. Still, the mere suggestion of an alien artifact sparked the public's imagination, cementing Oumuamua's legacy as one of the most enigmatic objects ever found. In contrast, 2I/Borisov seemed more familiar. Discovered in August 2019 by Gennady Borisov with a homemade telescope, this visitor looked and behaved like a typical comet in many ways. Borisov had a visible coma, a fuzzy halo of gas and dust, and a tail that extended millions of kilometers as it neared the sun. Telescopes quickly confirmed its path was hyperbolic, an open-ended trajectory that proved it came from interstellar space. Astronomers around the globe scrambled to observe it. The Hubble Space Telescope captured images of Borisov in late 2019, showing a bright core of dust and a stable coma. Unlike Oumuamua, which was elusive and detected only after it had passed the sun, Borisov was discovered inbound, giving scientists ample time to watch it evolve. They saw it brighten and then fade just like a normal comet. In early 2020, Hubble even noted that a fragment might have broken off its nucleus, again something not unheard of for active comets. Yet Borisov had its own surprises. Spectroscopic studies revealed that its chemical makeup was unusual. It was very rich in carbon monoxide, far more than any solar system comet at a similar distance from the sun. Carbon monoxide is a very volatile gas that requires extremely cold conditions to freeze into ice. The excess CO hinted that Borisov formed in a frigid environment, perhaps in the outer reaches of its home system, maybe around a cool red dwarf star or in a cold primordial disk of a young star. This was a tantalizing clue to its origin. If its cometary ices condensed in an extremely cold region, Borisov could be a fragment from the far outskirts of an alien solar system, a chemical ambassador from a place where ices we rarely see can survive. Researchers even speculated it might be a piece of a small, icy world or a fragment of a dwarf planet's crust, rich in CO ice. By the time Borisov swooped past the sun, reaching perihelion in December 2019, and headed back to the stars, it had provided a wealth of data. Its nucleus was estimated to be only about 0.9 to 1 kilometer across. It raced through the inner solar system at about 110,000 miles per hour, 177,000 kilometers per hour. And critically, Borisov demonstrated beyond any doubt that comets do visit us from other stars. Whereas Oumuamua appeared to be a rock, Borisov is really active, more like a normal comet. It's a puzzle why these two are so different, remarked one astronomer. The stark differences between the first two interstellar objects, one dry and asteroidal, the other icy and cometary, taught us that interstellar visitors come in assorted guises, reflecting the diversity of their origins. These early lessons set the stage. With two interstellar objects spotted back-to-back, scientists anticipated that more lay hidden in the cosmic deep. Surveys were expanding, new telescopes were coming online, and our eyes were open to the possibility of additional visitors. Indeed, astronomers suspected that in the vast reservoirs of comets in our own solar system, like the distant Oort cloud, some are occasionally flung outward to become wanderers in interstellar space. The wait for the next interstellar visitor was not long. In late June 2025, the ATLAS survey, a network of automated telescopes designed to hunt for asteroids on collision courses with Earth, picked up a faint moving point of light in the constellation Sagittarius. On July 1, 2025, the ATLAS telescope in Rio Hurtado, Chile, reported the object to the Minor Planet Center. At first glance, it seemed like just another new comet discovery. It was given a provisional designation C/2025 N1 ATLAS. But very quickly, as observatories around the world started tracking it, the truth became clear. This object was traveling far too fast and on too strange a path to be a local comet. Follow-up observations poured in, including pre-discovery images taken weeks earlier in mid-June. All data confirmed an open-ended trajectory. The object wasn't bound to the sun at all, it was merely paying us a visit. By July 2, 2025, the Minor Planet Center announced it as an interstellar object, formally designating it 3I/ATLAS, the third of its kind. There was excitement but also caution born of experience. We now knew interstellar objects come in different forms. What was 3I/ATLAS going to be like? Early reports suggested it possessed a fuzzy coma, hinting at a cometary nature. As more images came in, it was evident that 3I/ATLAS was surrounded by a cloud of dust, albeit a small one. It was not a stark point of light. It had the hazy look of a comet. The Atlas in its name recognized the discovery team, while the I stands for interstellar, and the 3 marks it as the third such object. Anticipation built swiftly. This time, unlike ʻOumuamua, we had found the visitor early, with months ahead of it moving through our solar system. The astronomical community mobilized rapidly, determined to study this alien wanderer in unprecedented detail. News of the discovery spread quickly beyond scientific circles. The world learned that yet another interstellar interloper had entered our cosmic backyard. Across continents, telescopes large and small tracked 3I/ATLAS against the stars, gathering photons that had bounced off a traveler born in a distant sun's embrace. Humanity was ready to learn whatever secrets this visitor carried. If we could trace the path of 3I/ATLAS through space, it would look like a vast open curve, a hyperbola, piercing the solar system. Unlike the closed loops of planets and ordinary comets, a hyperbolic trajectory is one of escape. This object came from afar, is cruising through our sun's domain, and will head back out to interstellar space, never to return. In practical terms, the sun's gravity is not enough to capture 3I/ATLAS. It's moving too fast and on too unbound a path. How fast? When 3I/ATLAS was first observed in June 2025, it was about 670 million kilometers from the Sun, near Jupiter's orbit, and already cruising inward. It approached from the general direction of the constellation Sagittarius toward the dense star fields near the Milky Way's core. As it fell toward the Sun, like any comet, it accelerated, trading gravitational potential for speed. By the time it reached the inner solar system, 3I/ATLAS was moving incredibly fast, over 130,000 miles per hour, 210,000 kilometers per hour, relative to the Sun, and climbing. For comparison, that's about 58 kilometers per second, faster than any spacecraft humans have ever launched, and a record among the 3 interstellar objects observed so far. Importantly, 3I/ATLAS's trajectory was not steeply inclined or perpendicular to the planetary plane. It was arriving on a path only slightly tilted relative to the ecliptic. In fact, its orbit is retrograde, moving in the opposite direction of the planet's orbits, but nearly flat along our solar system's plane. Some might call this a coincidence. Others note the plane of our solar system isn't far off from the plane of the galaxy's disk, so an interstellar object from the galactic disk might naturally come in on a similar incline. Nonetheless, such an alignment is statistically uncommon. For practical planning, what mattered to astronomers charting its course was that 3I/ATLAS would make a relatively gentle passage through the inner solar system. It was not going to come particularly close to Earth, at nearest about 1.8 astronomical units away, roughly 270 million kilometers, or 167 million miles, about as far as Mars is from us. In early October 2025, it would pass about 70 million kilometers from Mars, giving the fleet of spacecraft there a chance to observe it from a different vantage. Then it would slip behind the Sun from Earth's perspective in late October, surviving a perihelion at about 1.4 astronomical units, just inside the orbit of Mars, around October 29th. After that, it would swing back outward, crossing Venus's orbital distance, with Venus nowhere near that point, in early November. By March 2026, forecasts showed it passing Jupiter's orbit, on the far side from Jupiter itself, and continuing its escape. The Sun's gravity would bend its path but ultimately not hold it. 3I/ATLAS came in on a one-way ticket. The orbital eccentricity calculated for 3I/ATLAS was about 6.1, an extremely high value. For reference, a perfect parabola is approximately 1 and a circle is 0. This confirmed its status as a hyperbolic comet with a lot of excess velocity. In plainer terms, even after escaping the Sun's pull, it will still be moving at tens of thousands of miles per hour relative to the stars. Such speed can only be gained by being tossed out of another star's gravitational well long ago. This dynamical evidence, speed and trajectory, was airtight proof that 3I/ATLAS is not from here. No comet that originated in our solar system, even from the far Oort cloud, would naturally have such a hyperbolic orbit unless something truly extraordinary happened. Once 3I/ATLAS was identified as an interstellar interloper, an unprecedented observational campaign sprang to life. Space-based assets turned their eyes toward the visitor. The Hubble Space Telescope observed the comet as early as July 2025. The James Webb Space Telescope, JWST, with its infrared eyes, followed in early August. A UV-sensitive space observatory captured the subtle glimmer of hydroxyl in the comet's vicinity. Even spacecraft further afield joined the effort. The Mars rovers and orbiters prepared to snap images during its Mars-adjacent passage, and a Jupiter-bound probe planned an attempt to collect data as 3I/ATLAS passed by in 2026. It seemed every available eye in the solar system was turning to watch this small cosmic visitor. Never before had an interstellar object been observed with such a coordinated, high-powered fleet of instruments. Hubble's early images, taken when 3I/ATLAS was about 277 million miles from Earth on July 21, 2025, revealed a teardrop-shaped cocoon of dust surrounding a bright nucleus. Because Hubble was locked onto the speeding comet, background stars appeared as short streaks, a vivid reminder that this object was in motion, an interloper against the fixed stellar backdrop. From these observations, scientists began estimating the size of the comet's solid core. By late August 2025, data suggested the nucleus of 3I/ATLAS was at most about 5.6 kilometers, 3.5 miles, in diameter, and possibly as small as around 440 meters, a quarter mile, across. That upper estimate, a few kilometers wide, would make 3I/ATLAS several times larger than Borisov and vastly larger than diminutive ʻOumuamua. If 3I/ATLAS truly is approximately 3 to 5 kilometers in size, it would be by far the largest interstellar object ever detected. Some later estimates put it between 5 and 11 kilometers, though these numbers remained preliminary as observations continued. In any case, 3I/ATLAS appeared to be a significant hunk of material carrying perhaps billions of tons of mass from another star system. On the ground, large observatories got to work as well. The Gemini South Telescope in Chile captured a remarkable photograph of 3I/ATLAS in July 2025, showing a classic cometary appearance, a bright diffuse head and a faint tail trailing behind. At first glance, one might not distinguish it from a normal comet of our own solar system. It had a slight greenish tint in some images, a common feature of comets rich in certain gases, and as weeks went by, observers noted its tail grew in length. It even displayed an unusual phenomenon, what looked like a backward tail. Normally, a comet's dust tail is pushed away from the sun by radiation pressure, so it trails behind the comet relative to its path. But 3I/ATLAS showed a stream of larger dust grains being pushed in the direction of the sun by the comet's own outgassing pressure, essentially heavy particles expelled by jets that sunlight couldn't immediately blow away. This created the appearance of a secondary tail pointing sunward, a striking and rare sight sometimes called an antitail. It was a vivid display of how active 3I/ATLAS was, venting material vigorously as it warmed. Early on, 3I/ATLAS was indeed noted to be unusually active for how far it still was from what truly excites scientists about capturing an interstellar comet are the clues it carries in its chemistry. Here is an object formed around another star, preserving perhaps the very building blocks of its original planetary system. By splitting the comet's light into spectra and analyzing the gases it releases, we can read a chemical letter from a distant place. As one astronomer put it, when we detect water, or even its faint ultraviolet echo, OH, from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. In July 2025, ultraviolet observations detected a surge of hydroxyl OH molecules coming from 3I/ATLAS. O forms when water, H2O, is broken apart by sunlight's UV rays. Detecting OH around a comet is a proxy for detecting water, and it was seen when the comet was a remarkable 2.9 astronomical units from the Sun, nearly 3 times farther out than Earth's orbit. At such a distance, sunlight is weak, and typically water ice is still too cold to sublimate in large amounts for ordinary comets. Yet 3I/ATLAS was already gushing water vapor. Researchers calculated it was shedding roughly 40 kilograms of water per second at that stage, about the flow of a fire hose on full blast. The image of a fire hose of water blasting from an interstellar comet before it was anywhere near the sun captured imaginations and challenged models. This early water activity suggested intriguing possibilities. Either 3I/ATLAS had very volatile ice just below its surface, so that even a little solar warmth at 3 astronomical units released it, or it had an abundance of very small ice grains that heat up quickly. A study at the end of September 2025 provided clear evidence of distant water outgassing and proposed that tiny icy grains on the comet's nucleus were being warmed by sunlight and vaporizing to produce the observed OH signal. This hinted that comets from another star might have different textures or grain properties that affect how and when they release water. Meanwhile, the James Webb Space Telescope targeted 3I/ATLAS with its superb infrared spectrographs. Initial observations indicated that 3I/ATLAS has a high carbon dioxide to water ratio in its composition. CO2 ice sublimates at higher temperatures than water ice. The fact that CO2 seemed plentiful compared to H2O suggested that 3I/ATLAS might have formed far from its parent star, where CO2 ice could freeze alongside water ice. In our solar system, for instance, CO2 ice forms in the cold realms beyond Saturn. These data pointed to a comet rich in carbon dioxide and dovetailed with the early water activity. If it is losing water at 3 astronomical units, its ices likely include more volatile components like CO2 or CO that can jumpstart activity far out. Another curious detection involved nickel in the comet's coma, apparently without much iron. On Earth, nickel and iron are often found together. Some reports indicated nickel was observed outgassing with no corresponding iron line. One theory was that this could reflect origin in a metal-poor environment, as might occur around older stars. Others cautioned it might simply be that nickel-bearing molecules like nickel carbonyl sublime more readily than iron compounds. It's a technical point, but one seized by those inclined to speculate about artificial origins. However, mainstream researchers saw it as another piece of the compositional puzzle, likely explainable by natural processes given the right conditions. As the comet drew closer to the Sun through late 2025, astronomers monitored its evolution. Many expected it to brighten and perhaps develop a more prominent tail or a green glow as solar heating ramped up. The green color in comets comes from molecules like diatomic carbon or CN being broken apart by sunlight. Indeed, by October, some images showed a faint emerald hue, suggesting complex chemistry at work. In essence, 3I/ATLAS behaved like a dynamically young comet, one that perhaps had never been near a star since its formation. Every observation was a precious data point: the color of its dust, the ratios of gases, the shape of its coma, the flux of material. One of the most profound questions about an interstellar visitor is, where did it come from? With ʻOumuamua and Borisov, astronomers attempted to backtrack their incoming trajectories to identify candidate origin stars, but with little luck. The uncertainties were too large and the objects had been wandering too long, perturbed by unknown encounters. With 3I/ATLAS, an international team endeavored to do the same, using precise stellar positions and motions. By rewinding the clock on 3I/ATLAS's trajectory and checking it against the past motions of nearby stars, they hoped to pinpoint if it had passed near any star in the last few million years. The results were intriguing. Tracing 3I/ATLAS's path back some 4.3 million years, the study identified dozens of star systems that the comet had come moderately close to in that time. But none of those encounters could account for the comet's current speed and direction. None seemed to be the home that kicked it out. The gravitational tugs were negligible. This implies that 3I/ATLAS did not originate anywhere near our Sun or its immediate stellar neighbors. To explain its high speed and hyperbolic orbit, one must go back much further and likely to a far more distant origin. The researchers hypothesized that 3I/ATLAS is extremely old, perhaps having traveled on the order of billions of years through the Milky Way. One scenario that fits the data is that it was born in the formative days of our galaxy, in a region perhaps at the border between the Milky Way's thin disk and thick disk. The thin disk hosts most familiar stars, including the Sun, and is relatively young and metal-rich, while the thick disk is older and more metal-poor. The wild frontier between these two populations could be a place where dynamic interactions were common and where primordial objects could be ejected. According to one analysis, 3I/ATLAS may be on the order of 10 billion years old, more than twice as old as our solar system. If true, that is astonishing. A time capsule from the early Milky Way formed around a star that was among the first in the galaxy to have planets, or even from a protostellar cluster that no longer exists. It might have been wandering the galaxy since before Earth even existed. Over such vast time, it would have crossed spiral arms, passed near supernovae, through interstellar clouds, and experienced the subtle gravitational pulls of countless stars, a true galactic odyssey. How did it get ejected in the first place? The prevailing theory is that such objects start in the outskirts of a planetary system, akin to our Oort cloud, and are flung into space by gravitational interactions. In our solar system, many Oort cloud comets were likely thrown outward by close encounters with giant planets long ago. In the same way, 3I/ATLAS might have had a brush with a giant planet in its original star system, or a passing star perturbed its orbit, giving it escape velocity. Once adrift in the galaxy, it essentially became an ice rock castaway, destined to roam indefinitely unless captured or destroyed. Pinpointing a specific parent star for 3I/ATLAS remains highly uncertain and probably impossible with current data. Beyond a few million years, the cumulative effect of random tugs and the sheer scale of time erases the trail. So, while we likely won't ever know which star it came from, the evidence suggests a general origin, perhaps an ancient metal-poor environment in the outer reaches of the galaxy. This aligns with the chemistry hints. The high CO2 content and nickel/iron oddities might be fingerprints of a system with different elemental ratios. With 3 interstellar objects now in hand, we have the beginnings of a sample set, small but incredibly instructive. ʻOumuamua, a 100 to 150 meter shard, elongated, no coma, a slight non-gravitational acceleration, reddish surface, discovered post-perihelion and gone before we could study it in depth. Borisov, a textbook comet approximately 1 kilometer across, active with a visible coma and tail but unusually rich in CO, suggesting a frigid birthplace. Atlas, volatile rich, unusually active far from the Sun, possibly several kilometers wide, displaying anti-tail dust dynamics with a high CO2/H2O ratio and early OH detections at 2.9 AU. Side by side, they show a startling diversity, no two alike, implying that ejected planetesimals from other stars span a wide range of compositions and histories. One common thread unites them. Each became an exile through gravitational dances, giant planets and stellar flybys swapping material across the galaxy and connecting planetary systems through drifting messengers of ice and rock. The arrival of 3I/ATLAS ignited a flurry of activity not just in telescopes, but in the scientific community at large. Dozens of astronomers and planetary scientists specializing in comets, astrobiology, and planet formation turned their attention to this interstellar interloper. Within weeks of its discovery, analyses of its orbit, potential origin, and early spectra circulated widely. Public-facing tracking tools were updated so enthusiasts could follow its path in real time. There was a palpable sense of excitement. With an interstellar comet passing through our own solar system, it's as if a sample of a planet-forming disk from another star has shown up in our backyard. Researchers were keen to squeeze every bit of information out of it before it departed. International collaboration defined the campaign. Teams coordinated observation schedules across continents and wavelengths. Radio dishes probed gas signatures. Optical telescopes tracked brightness and structure. Ultraviolet and infrared instruments dissected the composition. The Minor Planet Center served as the clearinghouse for positional data, enabling precise trajectory updates that let even amateurs know where to point their telescopes. Public interest grew with each new discovery: water seen at great distance, CO2-rich makeup, a possible green glow, and headlines amplified the unfolding story. As with ʻOumuamua, speculation about alien technology inevitably surfaced. A provocative paper mused that 3I/ATLAS's low inclination, nearly coplanar path could favor a hypothetical probe using the Sun for a clandestine maneuver. The idea made waves, but collided with the weight of evidence. Everything observed about 3I/ATLAS looked like a comet and behaved like a comet. Detailed rebuttals noted that a low inclination can naturally arise for interstellar bodies originating in the galactic disk, that the hyperbolic speed and eccentricity match gravitational ejection expectations, that the odds of close planetary encounters were low and unremarkable, that the colors and spectra matched known comet classes, and that no anomalous accelerations suggesting propulsion were detected. Extraordinary claims require extraordinary evidence. For 3I/ATLAS, the evidence points firmly to a natural origin. Culturally, interstellar objects rekindle a sense of wonder about our place in the cosmos. People ask, Could such comets ferry life's ingredients between stars? While 3I/ATLAS is far too cold and airless to harbor life, the detection of water and organic bearing molecules underscores that the building blocks of biology are widespread. In a real sense, these visitors bridge hard data with philosophical reflection. They remind us that the universe trades materials across light years, and occasionally one such messenger drifts past for us to study. As 3I/ATLAS continued on its way, past Mars's orbit in early October 2025, around the Sun in late October, outward again toward the dark, its legacy came into focus. It left a trove of scientific data, evidence that even an ancient comet carries water and carbon across the stars, motivation to broaden theories of comet activity to include vigorous outgassing far from the Sun, hints that a comet's chemistry can encode the structure and history of the Milky Way itself. It also showcased humanity at its collaborative best, telescopes on Earth and in space working in concert, professionals and amateurs sharing the sky, all focused on something not of this Earth and not of this Sun. Looking forward, many expect a golden age of interstellar object studies. New wide-field surveys will likely find more, perhaps many more. Missions like ESA's Comet Interceptor, designed to wait in space and sprint to a newly found comet, may one day rendezvous with an interstellar target. Imagine holding a sample from another star system, alien ice and dust formed in a faraway dawn. Until then, we rely on telescopes and clever analyses, and even with those alone, look how much we've gleaned. Cold, CO-rich nurseries around other stars inferred from a single passing object, textures of cometary ice hinted by OH at 3AU, a time capsule perhaps older than the solar system itself drifting briefly into our ken. There's a humbling aspect to it all. These objects are small and faint. Without diligent surveys and a dash of luck, we would never notice them. ʻOumuamua slipped by after the fact. Borisov was spotted by a patient amateur. Atlas was found by a system designed to protect Earth that happened to net a traveler from another sun. It suggests our catalog is just the tip of the iceberg. Perhaps they inspire kinship with distant worlds. In a universe that can feel isolating in its vastness, these drifters are reminders that we are connected to the galaxy by threads of wandering ice and dust. The camera of imagination follows 3I/ATLAS as it leaves our solar system, the sun dwindling behind, the infinite night ahead. Will it wander for another billion years? Will it pass some other inhabited world and spark curiosity there as it did here? In the silence of space it carries on, a voyager from an unknown dawn, a messenger of the stars, and a reminder that the cosmos is richer and more wondrous than we ever believed.